Okay, hello and welcome back everyone. Moving on to the next section is going to be convergence tests for infinite series. In many ways it's going to feel just like the last video, right? Something I've really been trying to stress the entire semester that you're probably more than used to now is the equivalence between something like an integral of a function and a sum of a sequence. They kind of play the same role, one of them being discrete, at least in its domain, and the other one being continuous in its domain. But in terms of infinite series, that's the name we give to a sum where the upper or lower bound is infinite. This is going to be basically the same as an improper integral of type 1, where we allow one of the bounds on the integral to be infinite. And just like we saw in the last video, all sorts of these tests that we can apply to testing the convergence of an improper integral, we can do the same sort of thing with infinite series. Now, I do want to reference the motivation for these convergence tests to be the same as that with the integrals. One of them being that an equilibrium for discrete dynamics is found by taking the limit as your time goes to infinity of the solution to the dynamics, but the solution always looks like a sum where time is playing the upper bound in the sum of some sequence. And of course, this is precisely the definition of an infinite series. And if this is equal to some equilibrium value, we would like to know. And in some cases, as with integrals, you just don't know how to actually compute the infinite series as is. What we have to put up with then is just being able to show that the infinite series converges, and then maybe by some other means, approximation means or experimental means, we can kind of get a good idea of what that convergent value should be. Or in other words, if we know it diverges, we kind of know it's a task that's not possible to try to find some value to predict long-term futures. So these are really good things to know about series, kind of independent of the equilibrium. It's just kind of a mathematical curiosity, and we'll see even in the next section why they're important, independent of equilibria. But when it comes to equilibria, it's important to know just whether or not some sort of future prediction actually will settle into equilibrium, or if it'll never settle to equilibrium and we're never going to try to find it. The first test we're going to see is going to be slightly modified from any of them that we saw in the last video. For the most part, we'll have the same test as in the last video, but in the discrete setting. The first one's really cool because it's called the integral test for infinite series, and it really does combine the two of them together. And so what we're going to think is we're going to think about having a sequence which is defined as a function on the integers. But suppose that this function, even though the sequence only sees f on the integers, suppose f can be evaluated on any real number. That's what I have there in the domain. And moreover, is differentiable. So you can take a derivative. Even more than that, you need that the derivative is actually negative. You need that the output of the function, there's my codomain, I'm saying that that's the non-negative real numbers. So more or less we're saying f is positive and decreasing. Pretty strong collection of properties for a function, but we'll see they're somewhat common that have these properties. So suppose we have some sequence A, and it happens to be equal to a function which is positive and decreasing. Then what we can claim about the convergence or divergence of the infinite series of A, this is actually the exact same as the convergence or divergence of the infinite integral or the improper integral of f. And so you can directly compare the series to the integral so long as, well, the sequence is actually equal to the function at the integers and the function is positive and decreasing. What's the most common situation of this? Kind of the classic choice that everybody brings up. We look at maybe 1 over n squared, n going from 1 to infinity. Now, if we recall way back from the first equilibrium chapter, we do actually know this is equal to pi squared over 6. This is known as the Basel problem. So it does converge, but let's assume that we didn't know it converged. Is there any easy way to actually determine that it converges? Well, because the function f of x, which is equal to 1 over x squared, in your head, you should be able to see how 1 over n squared and 1 over x squared are basically the same objects. It's just that the n squared version is only applied to integers and the x squared version is applied to all real numbers. So we look at the function 1 over x squared. Well, this function is positive, and if I look at the derivative, you can compute a derivative, that's really x to the negative 2 power, so you're going to get negative 2 over x to the third power. Well, because of that negative sign up front, at least when I'm considering, out to infinity, positive infinity, eventually this is strictly less than 0, is negative. We can go ahead and test the infinite series from 1 to infinity of 1 over n squared by computing the infinite integral from 1 to infinity of 1 over x squared dx. Well, what is that antiderivative? That's x to the negative 2 power. The antiderivative is negative 1 over x. I'm going to evaluate at my bounds 1 and infinity. If I plug in infinity, I get 0. If I plug in 1, I get negative 1 over 1, or in other words, this is 1. So this converges because 1 is finite, which means that my original series also converges. Going back to my classic testing whether or not it's raining before we know if I'm using an umbrella, testing that the integral converges is just half of showing it's raining. The other half actually comes here. This is also showing it's raining. We have quite a few separate steps to show that it's raining here. You have to show that the function is positive, its derivative is negative, and you have to show that the integral of that function converges. So it's kind of 3 pieces. So I say if f positive, f prime negative, convergence of the integral. There's the 3 pieces of what I would like to show is true. Then I can make my conclusion, which is that this converges, or my conclusion is that I use an umbrella. That's how we would use the integral test for infinite series. Pretty easy if you happen to find a function that satisfies all those properties and you know how to integrate that function. Classic case on why we might actually use this, I'll go back to that pretty picture later. Classic case on why we might actually use this is our p-test. Same p-test we have, but now we have it for infinite series. How do I show that the infinite series 1 over n to the p converges when p is greater than 1? You just show this because the integral test and the integral p-test. Right, so the fact that we covered the p-test for integrals in the previous section means that we can apply the p-test for integrals to this series as long as the integral test that we just covered works. And so we get exactly kind of the first case of the integral p-test, which was the case when the upper bound was infinite. We get that for infinite series as well, which means that power p, we're going to converge when the power is greater than 1, but we'll diverge if it's equal to 1 or less than 1. So we do have the exact same p-test, at least in terms of an upper bound of infinity. Let's go back to this really pretty picture that I have here. This is a visual representation for why the integral test works. We should think about the area that is on the far right side. This is really the area from some minimum value to infinity of f of x minus 1 dx. And then directly below that, we happen to have really a sequence or a sum from some minimum value out to infinity of a sub n. And then directly below that, we happen to have an integral from some minimum value to infinity of a function of x. And then directly below that, we have a different sequence from the minimum value out to infinity a n plus 1. And then the very bottom term here is kind of me shifting my function one more time to an x plus 1 dx. You can see basically that each case dominates the last in terms of actual area, if I look at the areas of all of these. And because they dominate each other, you can basically say, oh, well, the area of that term at the very bottom has to be less than or equal to the area of this term, which is less than or equal to the area of this term, which is less than or equal to the area of this term, which is less than or equal to the area of that term. And because of that, what you get to do is you can compare this infinite sum to kind of the convergence properties of the infinite integral that are on either side of it. They're flanking it. And so they all either converge or they all diverge. And the same thing actually with this integral. You can show that the integral will converge or diverge in equivalence to the infinite sum. And so you get this kind of nesting of all the sums and the integrals in terms of their areas. And because of that beautiful nesting, that's why we know the integral test actually works. So moving on past our p-test, we actually do recover the exact same direct comparison and limit comparison test that we had for integrals. So everything really does look the same here. I'm just replacing functions with sequences. You can see I'm trying to compare one sequence to another, and they both have to be positive. And if I know that one of them is bigger than the other, then in fact I know that the infinite series of one will be bigger than the other. But it's important in the same way that if I want to show, an converges, I must find a Bn which is, first of all, bigger, and second of all, also converges. Right? That's kind of what we needed out of the integral comparison test. And then you flip it for the other case. So when you do converges, you find the bigger sequence. If you want to prove diverges, you would say, maybe if I want to prove Bn diverges, I need to find An, which is, first of all, less than Bn, and second of all, also diverges. Because if I can push the value of An out to infinity, and I know that this series happens to be larger, it's also going to diverge. Okay, let's look at an example of this direct comparison test for infinite series. And the infinite series we'll look at is this one, which is a ratio of a square root of a quadratic divided by another square root of a quadratic. There's basically no way we'd be able to actually find an indefinite sum that we could then take out to infinity to see what the actual value of this infinite series is. Nonetheless, we should be able to tell if it converges or if it diverges. And the way we're going to do this, at least using a comparison test, is, as always, we'll need some sort of intuition as to whether we think this converges or diverges. And in this case, to obtain that intuition, let's just look at our actual function and think about taking n out to infinity, taking a limit as n goes to infinity. How would we take limits of algebraic ratios? We almost always look at the highest powers in the numerator and the denominator. Well, in the numerator, our highest power is n squared. In the denominator, it's n to the fourth. But let's make sure we include these square roots in both cases, because square roots really are playing the role of a 1/2 power, right? So we'll take n squared and a square root in the numerator, and an n to the fourth and a square root in the denominator. That's going to give me, when I simplify the numerator n and the denominator n squared, everything simplifies to 1 over n. And so we're thinking in our heads that this infinite sum is approximately going from 2 to infinity of 1 over n. Now, does that series converge or diverge? This series will diverge. And there are multiple ways of thinking about it. We can go back to our integral test. One of them, we think maybe the integral from 2 to infinity of 1 over x dx, which happens to be the natural log of x at 2 and at infinity. Well, the natural log is infinity at infinity, and so we get divergence on the natural log term there. Or we could have just thought about this with the p-test. What is the power on n? The power is 1, and because p equals 1 says diverges for the p-test, we're going to see that this sum diverges. Now that's going to give us some intuition, gives us a really good guess about the sum that we're actually curious about. We're going to have to prove that this diverges. Now that we have the intuition, we have to go ahead and prove it. If we're going to use the direct comparison test, let's go back to what this looks like. We've got this nested collection of inequalities. If I want one of these terms to diverge, well, I'm going to ask for the bigger one. Maybe I want to see if this diverges. So I'm going to find something smaller that also diverges. And that something smaller almost always will be at least similar to our intuition step, our intuition in this case being 1 over n. Ideally, we can show that 1 over n is smaller than this ratio. But it's not going to be an easy task, so let's try to talk about how we would show anything is smaller than that ratio. We'll show anything smaller than the ratio. I'm going to do my best to simplify the ratio. So let's try to simplify. We might not do a perfect job, but we're going to do the best we can. I'm going to look at this first case, n squared plus 2n plus 1. Those coefficients 1, 2, 1 should feel pretty familiar from Pascal's triangle. It's the second row of Pascal's triangle. It's telling us this is actually a perfect square. So we can compute it as a perfect square, n plus 1 squared. Equivalently, you can think about this as completing the square, right? We did that when we were doing trigonometric substitution. In the denominator, it's not going to look quite so easy, but because it's a 4 and then a 2, and really that's n to the 0 power at the end there, we should think about this denominator really also as a quadratic, but it's a quadratic of the variable n squared. And so we've got n squared squared, that's playing the role of n to the fourth, and n squared is in the middle, and then n to the 0 power at the end. So if we, kind of complete the square, on this quadratic, where really the entire n squared term is playing the role of my variable, go through the complete the square process with a being 1, b being -2, and c being -2, you're going to find out you have a coefficient of 1 out front, a subtraction by 1, and then a subtraction of 3 at the end. And so you complete the square in the denominator, you're going to get root n squared minus 1 squared minus 3. The numerator, because you have a square of a perfect square, those will cancel, you just have n plus 1 in the numerator. The denominator is kind of stuck, so how could we do something with the denominator? Well, what we're actually going to do there is we're going to go ahead and try to actually pull off some inequalities. Because the whole point of working with a comparison test, or a direct comparison test, is to extract these inequalities. And primarily you're thinking about that inequality of starting with b, and you're going to end up with something smaller than b. So how could we make this denominator, how could we modify it to make the overall term smaller? Well, let's think about a -3 in a denominator. If you have any positive number, maybe -1 in a denominator, maybe your positive number should be at least 2, of course, but as long as you have basically a positive number, -1 in a denominator, if you go ahead and drop a subtraction by 1, well, you've just dropped something that had the denominator smaller, so now your denominator is larger. This is now larger, but in the denominator. Something larger in the denominator overall is smaller. And so by dropping negatives, or really by dropping minuses, from a denominator, we get smaller. Which means I can go ahead and drop that -3, and all the price I have to pay for dropping a -3 is getting smaller. So you get smaller by dropping -3. What's happened to the denominator? Now it's the square root of a square, and the square root and the square cancel. We just end up with n plus 1 over n squared minus 1. Could I simplify this anymore? Well, I guess my denominator is a perfect square, so I could, I suppose, simplify this to n minus 1, n plus 1, and go ahead and cancel these two terms, and I'm looking at 1 over n minus 1 for my other sum. Or you can do what I ended up doing at the bottom, which is, hey, every time I drop a negative from a denominator, I get smaller. There's a negative in the denominator, so I'm just going to go ahead and drop that negative from the denominator and just call it n squared at the price of saying that I get smaller. And so I'm just going to get smaller again by moving my denominator to n squared, and then I can go ahead and distribute that denominator to both terms in the numerator and simplify, and I find out that I have 1 over n plus 1 over n squared. So in other words, this original ratio of square roots of a quadratic and a square root of a quartic is actually greater than, and greater than are equal are both good enough in the comparison test world. They're both going to be greater than 1 over n plus 1 over n squared. And what happens when I decide to actually compute the infinite series of 1 over n plus 1 over n squared? Well, the nice thing about series is that it's linear, so I'm just going to distribute that series to each term individually. I have the series of 1 over n and the series of 1 over n squared. And what do we know? 1 over n diverges. 1 over n squared happens to converge, but I don't really care, because if I take infinity and I add some finite number to it, like 1 or whatever, it's still going to be infinite. I'm still diverging at the end of the day. And so what I've shown here, this is me showing half of its reigning. The fact that I've shown that my series diverges is me showing the other half of its reigning. And so what do I get to conclude after I've shown both parts of its reigning? I get to conclude that yes, my overall infinite series diverges because it's bigger than another diverging series, namely 1 over n plus 1 over n squared. So that's how we use the direct comparison test for sequences. Should feel basically the same as with functions. Now the limit comparison test is also going to be the same as functions. We're going to test the ratio of two sequences, a divided by b. We're going to take its limit out to infinity. We're hoping that that's a positive finite constant, just like with our functions, and the result's going to be the same as the limit comparison test with functions, which says the convergence or divergence of one of them will be exactly the same as the convergence or divergence of the other. So one completely determines the other as long as their limit is a positive finite constant. What would that look like if I wanted to actually use it to prove something? Well, here we've got an infinite series. I've got n to the 1/2 in the numerator, n to the 6 plus n third plus 1 to the 1/3. And I want to test whether or not this converges or diverges. Well, I'll need an intuition again. So let's go with highest powers. In the highest power, my numerator, n to the 1/2, nothing I can do about that. In the denominator, I have n to the 6th, but there's also an n to the 1/3 going on, so really I have n to the 6th to the 1/3 in the denominator. Numerator stays the same for now. The denominator, I'm going to multiply that 1/3 by the 6 and get n squared out of this. If I take a 1/2 in the numerator and a square in the denominator, well, that's 1, 2, 3, 4 copies of 1/2 in the denominator. One of those 4 copies will cancel with the numerator, and I'll have 3 copies of 1/2 in the denominator. And so this is behaving like 1 over n to the 3/2. And does that series converge or diverge with the 3/2? Well, let's think about the p-test. P is 3/2. That's bigger than 1, so we converge. Alternatively, if you forget how the p-test works, just go ahead and integrate it. If I integrate 1 over x to the 3/2, I'm going to end up with 1 over x to the 1/2, and then maybe there's a 2 out front here, negative 2 out front technically. But if I evaluate that at the lower bound of 5 and the upper bound of infinity, because that 1/2 is in the denominator, I'm getting 0 minus negative 2 over root 5. And so this is finite. So however you want to think about it, converges. So our intuition here is that this also converges. Now that we have intuition, we can actually use the limit comparison test. What do I want to compare in the limit? Well, the fact that I was approximately equal to 1 over n to the 3/2 is a good choice for the limit comparing sequence. So let's go ahead and actually choose 1 over n to the 3/2 as our sequence we're going to compare in the limit. And the limit comparison test says I'm just going to compute the limit as n goes to infinity of an divided by bn, where maybe I choose an as 1 over n to the 3/2. So there it is. And then bn, of course, has to be everything in my original sequence. And so I've kind of shoved it all in there into that denominator. But, you know, the original series was n to the 1/2 over n to the 6 plus n cubed plus 1 to the 1/3. So I've just taken this entire term and thrown it in the denominator here. And then I just have to simplify to actually compute this limit. So I've got a denominator in the numerator that's going to jump down to the actual denominator. I've got a numerator in the denominator that's going to stay in the denominator. And then I've got an extra denominator of a denominator that's going to move up to the numerator. And so that'll be how I switch everything down to a single fraction. And at this point, I can combine my terms in the denominator. That's going to be n squared because I'm adding those exponents. I then maybe want to combine everything in terms of this power 1/3. So how could I write n squared as a 1/3 power? Well, you can write it as n6 to the 1/3. If I write it as n6 to the 1/3, now everything is to the 1/3 power. I can pull that 1/3 power out, and what's on the inside is just n to the 6 plus n cubed plus 1 over n to the 6. I can now distribute this denominator to each term in the numerator. I have n6 over n6, n cubed over n to the 6, and 1 over n to the 6. If I simplify those a little bit, well, n6 over n to the 6 simplify to 1, n cubed over n to the 6, 3 of those are disappearing. I'll just be left with n cubed in the denominator, and nothing simplifies in the third case. What happens when I take my limit at infinity now? Well, 1 over n cubed becomes 0, 1 over n to the 6 becomes 0. I'm just left with 1. And what does the limit comparison test need that limit to be? That limit has to be a positive finite constant. What do you know? The number 1 is definitely a positive finite constant. And so this number 1 that I just achieved, I can say yes, is a positive finite constant. This is me showing that it's raining. So then I can go ahead and conclude that the convergence of 1 over n to the 3/2, which does converge by the p-test, implies the convergence of my original series, which is a lot harder to actually calculate. So that's a lovely example of the limit comparison test. And of course, we do have the ratio and the root tests. We'll start with the ratio test. This one does look different, right? So I do want to point out this does look different than the ratio test for functions, which had f prime of x divided by f of x. You would take the limit as x went to infinity, and this was equal to L. And more importantly, when it was equal to L for functions, that L changed behavior at 0. Where in our case, we're computing an plus 1 over an. That's definitely not the derivative. And I'm calling it equal to L, but where's L changing behavior? It's changing behavior at 1. not 0. And so things look a little different in the ratio test when it comes to sequences. Primary reason why it looks different, there's no such thing as the derivative for sequences, right? So we can't put a derivative up top. Let's say we did put the closest thing we had for derivatives up top. It's delta an over an. You could actually make the statement about, the limit of delta an over an as n goes to infinity. If you wanted this to be equal to L, then you could modify these to zeros and everything would work. It's just that this computation is kind of one extra step of computation, right? That finite difference is going to take you a little bit of work. If you go ahead and rearrange what this is actually trying to say, because the finite difference, delta an, is an plus 1 minus an, that numerator over an, if I divide this by an, well, what do I get? I get an plus 1 over an minus, well, an over an will just be a 1 here. And so, what is a minus 1 when the right-hand side is 0? We could add 1 to both sides, and you're just swapping the 0 on the right-hand side for 1 on the right-hand side. So that's where that 1's coming from, and you're just saving yourself a little bit of time, not computing the finite difference, by just saying it's the next term in the sequence. So they do happen to kind of be the same statement. They look different, and this one actually is a lot less work because you don't have to compute the derivative like you did with the function or even the finite difference. So this is just a little bit easier version of a ratio test that we can use for infinite series. Now what we care about is we compute this limit of an plus 1 over an, and we see what it's equal to. We then test if that number is greater than 1. Once again, this is like exponential growth. Exponential growth is going to diverge. If that number is equal to 1, it's like growth or decay, but not exponential, so we don't really know much about it. So we can't determine the convergence when it's non-exponential. And when that number is less than 1, we have like exponential decay, and so our series converges. Let's look at a nice example of using this ratio test. It's going to basically behave the same as our example did before, except we kind of get to play games with factorials in ratio tests, which is pretty fun. So I'll mention this really quick. The ratio test works really well with factorials. And so if you ever see a factorial in an infinite series, you're going to want to think about using the ratio test. Reason being that, let's recall n plus 1 factorial divided by n factorial. This is kind of the point of the ratio test, right? You add 1 to it, and then you divide by the current one. Well, n plus 1 factorial, you can define every factorial, right, as a multiplication of all of the descending terms, and then the n factorial in the denominator, also a multiplication of descending terms. But what you're going to get when you just add 1 to it is that n will cancel with this n minus 1 with that n minus 1. In fact, they all cancel, except for the only term that won't cancel will be the original n plus 1, kind of the extra case factorial. And so that's why factorials behave really, really well. That's why the example I've provided for you here is going to test the convergence of this series using factorials. It's really quite interesting because we've got exponential growth in the numerator, but we are dividing by factorials. So in some sense, if this converges, it says that factorials outgrow exponentials. If you thought exponential growth was strong, we're going to see that this does converge. If you thought exponential growth was strong, it turns out factorial growth is insanely strong. So really cool way to see that you actually get factorial growth, and when you put in the denominator factorial decay, it's a really, really powerful decay mechanism to force a lot of convergence. Let's go ahead and use the ratio test. Let's recall what the ratio test is asking me to actually compute. The limit of an plus 1 over an. I want this to be equal to L as I let n go out to infinity, a of course being that in this case, the ratio e to the n over n factorial. So an plus 1 will be e to the n plus 1 over n factorial. An will be e to the n over n factorial. And then I'm going to want to go ahead and simplify this quite a bit. When I simplify that, as always, I'm looking in, well, the denominator of the numerator goes in the overall denominator. The denominator of the denominator goes in the overall numerator. The numerator of the numerator goes in the overall numerator. And the numerator denominator goes in the overall denominator. Okay, so my numerator will be e to the n plus 1 times n factorial. Denominator will be n plus 1 factorial times e to the n. Well, basically what we're going to see is that these factorials play nicely with each other, so I've grouped them together, and the exponentials play nicely with each other, so I've grouped them together. Why do they play nicely? Well, this is e to the n divided by e to the n. Those cancel. There's just one extra copy of e sitting around there. And then, as I already kind of mentioned with these factorials, an n plus 1 factorial has exactly one extra term that the n factorial didn't, and it has, the very top term. But everything else is the exact same in those factorials, and so everything else cancels. We're just left with an n plus 1 in the denominator. So this simplifies to an e divided by n plus 1. And I'm going to go ahead and take a limit as n goes to infinity of e over n plus 1. Well, e is finite, right? It's just 2.718 dot, dot, dot. Well, that n plus 1 is going to infinity plus 1. This whole thing is going to 0. The fact that the whole thing went to 0, let's go back to my limit comparison test. How does 0 compare to the number 1? Well, 0 is absolutely less than 1. And so we're in the very bottom case, we find out that our series converges. And so what we have over here is a series which converges because that 0 is strictly less than 1. Finally, we have our root test for infinite series. It's going to look the exact same. Kind of the main difference, I've put absolute value signs around my sequence. That just makes my life easier, keeps everything positive for me. But I'm still just going to take the sequence to the power 1 over n, which is called the root test because it's the nth root of my series. I'm going to take the limit as n goes to infinity. We're going to get the exact same results as we had for functions, which is to say if this output L happens to be greater than 1, we have exponential growth. So we diverge. If it's equal to 1, we have either growth or decay. Neither are exponential though, so we cannot determine the convergence. We have to use a different test. If L is less than 1, then this series will converge because we have exponential decay. And so everything looks exactly the same in this case. Let's just jump over to a lovely example. Our lovely example is going to be to test the infinite series e to the root n squared minus 2n plus 2 all over n. So we have some sort of exponential growth in the numerator and dividing by n in the denominator, so polynomially. This feels like it'll probably diverge because we have growth in the numerator and just algebraic decay in the denominator. So let's actually see that this will diverge for us by using the root test. So the root test says we're going to grab that sequence inside and we're just going to put it in absolute values and then take 1 over n on it. But of course, 1 over n on a ratio, this can just distribute to the numerator and the denominator individually. If I look at my numerator, I've got an exponential to the 1 over n, and then the denominator, that's n to the 1 over n. Everything's positive here, so I'm going to drop my absolute value signs. And because this is an exponential to a power, I'm going to take this power and I'm going to multiply it against what was already in the exponent. Of course, multiplying 1 over n, that's going to put an n in the denominator of that exponent. And then I'm just leaving my denominator as n to the 1 over n for now. Let's go ahead and compute the limit of each of these individually. So the first limit we'll compute as e to the root n squared minus 2n plus 2 all over n. Well, I could bring this n into the square root, in fact, into each term in the square root by paying the price of, the anti-square root, which is the square. So I've just brought it in as an n squared. That's going to give me e to the root n squared over n squared minus 2n over n squared plus 2 over 2n. And the only term that'll survive is this first one where n squared over n squared is 1. Everything else will be 2 over n and 2 over n squared, which if I take the limit as n goes to infinity will both give me 0. And so this will end up as e to the root 1, also known as e, also known as, never forget this, approximately 2.718, some finite value. In terms of the denominator, n to the 1 over n, if I want to compute that limit, it's a little tricky to know how to compute this limit. My favorite way of computing it is to rewrite kind of this base. The base of my exponent is n no longer is an n. I want to call it e to the natural log of n. Because if my 1 over n is in the exponent, I would appreciate all of my n's to be in the exponent. So I'm going to push the n in the exponent by doing e to the log. And then when it's e to the log, that's really going to multiply 1 over n. We're looking at e to the log n over n. How could I compute this limit of log n over n? Well, if I evaluate at infinity, log at infinity is infinity, and n at infinity is infinity. So that's an indeterminate form. I'll have to use L'Hopital's rule, which is going to tell me to take a derivative of the numerator. A derivative of natural log happens to be 1 over n, and then a derivative of the denominator, the derivative of n is 1. So that's really telling me that the limit of log n over n is really the limit of 1 over n over 1, which is just the limit of 1 over n. If I take n out to infinity, that happens to be 0. What is e to the 0? Well, e to the 0, just like anything else to the 0, is 1. And so we find out that the numerator here, right, we calculate the numerator as e, and the denominator here we just calculated as 1. And so this ends up in the limit being e over 1, also known as e, also known as 2.718 dot dot dot. Well, how does that value compare to what did the root test need? The root test said, how does that value compare to 1? Which of these cases is it? Well, 2.718 is definitely greater than 1. And so it turns out that we diverge. Not really surprising, since we noticed it behaved approximately like exponential growth there and just algebraic decay. But good to know and good to see we can do it with the root test. All right, just as before, I decided to add a little bit of intuition on when to choose which test in these cases, because there are a lot of tests. I think it's almost easier to know in the case of series which test to use, because the ratio test works super well with factorials. The root test works super well with exponentials or approximately exponential functions. And if it's algebraic, neither of those two are going to work well. You're going to want to use the limit comparison test when you're algebraic. So that's basically the three you're going to want to think about. I know everybody hates the direct comparison test, but it can be useful, as I mentioned before, with logarithms or something like that. I would save it to the end, though. I would try to use ratio for factorials, roots for exponentials, and limit comparison for algebraic. That's really the right way to do it. And then I do want to finish this section by mentioning that a traditional calculus-based course will include discussions on alternating series tests and absolute versus conditional convergence. We just didn't have the time to get to those sorts of tests in this class. But if you are ever interested in those or going to take some future calculus courses, I do suggest maybe going to Wikipedia and just seeing what those are about. They're nothing too crazy. It's just something I didn't want to necessarily discuss because the rest of these tests are a lot stronger. They are more powerful than either of these, and so I think give you a better idea of what it means for these series to converge. Anyway, that's all I've got. Next section is going to be my favorite one of the entire semester. We're looking at the Taylor series, generating functions, and power series, but primarily the Taylor series is what I think is one of the crowning achievements of a Calculus 2 course. I'll see you then. Bye.